All right, Unit 1, Lesson 10. This is the last one we're going to cover for our Algebra 2 unit here. So for our final one, we're just talking about different situations and sequence types. Now, I know coming up, you're going to have a unit test or something that you need to prepare for and have some stuff. So you might want to just make sure the same kinds of things that we talked about in Lesson 8 and Lesson 9. So some structure about what those explicit or nth term equations look like, and how those nth term or explicit equations look different for arithmetic versus geometric. We've been talking about that since the very beginning, so it's good to just make sure you have a good review of that. Remember, arithmetic is something that shows up where you're just going to be adding something over and over again. So our nth term equation is going to look like this, where we're going to have it times n, or the n minus 1. And we should be able to plug in whatever we want for n. And then just remember, you're going to follow order of operations. Okay, so if we want to find the 8th term, we're going to plug in 8 for n to figure it out. Now, on each of those things, we have whatever is our starting amount, whatever is our first term. We have whatever is our change that's happening. This is a constant. So we're either adding something or we're subtracting something, the same thing every time. And we're going to use this format if we start with a 0 term. So if we start with the 0th term, like in the last lesson, we talked about how we start with a cake in a room and then someone comes in and takes a third of the cake. So we have a starting cake. That's before anybody comes in and does anything with it. So that's a 0 term. But we have other times that we start with the first term and it's labeled as number 1, right? So this, for example, starts with a 0th term. We have a starting place of our population and then it grows from there. But if we have a geometric sequence like this, maybe we're going to call this our first term, and this our second, and our third, and our fourth, and our fifth. The equation is mostly the same, but a little bit different, just a small bit. Geometric, same kind of idea. We're still going to have our starting amount, so I'm going to put that in red because I'm a color coding lover, right? Whatever is our starting amount. However it's changing, this is going to be a multiplier. We've also called that a growth factor. We talked what that might be. So that multiplier that's happening, that's again, how is it changing? And then the same kind of thing. If we're starting with a 0th term, we're going to just have an n for an exponent. And if we start with the first term, we're going to have an n minus 1. Okay, sorry. Just got interrupted by a knock at my door. All right, so this might be helpful. Again, this is a 0th term if we start with the 0. And this is if we start with a first term. So good notes and examples. And again, maybe you also want to put an example like this on a help sheet or something to help you as you review. 10.1 gives us a geometric sequence and asks us just to recall how we find growth factor. So if we know it's geometric, we know we're using multiplication. We can think about it this way, that 16 times something equals 24. And the same is true with any two numbers next to each other, right? They all have to be multiplying by the same number. So 36 times something has to equal 54. And so to find that unknown something, we're going to use opposite operations. In this case, I'm going to divide both sides by 16. And when I do 24 divided by 16, I get 1.5. Oh yeah, because it's growing. It's getting bigger. There we go. I almost scared myself. I was like, why is it bigger than 1 if I'm trying to make something smaller? But I'm not. It's a growing function. So this is multiplying by 1.5. Okay. And I should see the same exact thing from 36 to 54. That if I do 54 divided by 36, again, 1.5, because it's consistent. It's multiplying by the same thing every time. One way to describe its growth is to say that it's growing by what % each time? What number goes in the blank for that sequence 16, 24, 36, 50, and be prepared to explain. Well, if it's got a 1.5 multiplier, and I'm turning that into a percentage, what this is saying, that 1.5, this is going to just help us refresh how to turn a decimal into a percentage. We just need to multiply it by 100. Or some people, like me, learned it by moving that decimal 2 times to the right to give us 150. Okay, multiplying this by 10 would give us 15. Multiplying it by 100 gives us 150. Okay, and that a way to think about that is that it's going by 150%, but it's keeping the 100% that it starts with. It keeps all of that, and it adds or grows by 50% on top of it. So that's how I would fill that in. It grows by 50% each time. Now this is how you can make some statistics sound pretty misleading or difficult to interpret, because something might be a very small change, but if I say it's growing by 50%, well then it sounds really urgent, like something I have to take care of. So just a reminder that we can take a decimal, multiply it by 100 to get a percentage. We can take a percentage, divide it by 100 to make it a decimal. And then we use that decimal as our multiplier. Just like up here, 1.5 was our multiplier. It's kept the 100% that it started with. So 16 keeps that 16, and it adds half of itself on top of that. Now half of 16 is 8. So 16 plus 8 gets you 24. And the same thing to get from 24 to 36. If I keep all of that 24 and I add half of itself, that's 24 plus 12, gets me 36. So that's what they're asking us. Now they would use this for something like population growth. Because if we have a growing population, we have to start building stuff well in advance. So we need to be able to anticipate when a certain population would reach a certain level that we need to do something like open a second high school, or add an extra fire station, or maybe we need to give a reason why we want another grocery store or supermarket. So companies are doing this all the time when they're trying to find what new markets they should get into. So the table shows 2 animal populations growing over time. Are the sequences represented by population A and population B arithmetic or geometric? Explain how you know. All right. I always go with arithmetic first because addition is always easier to me than multiplication. So I'm just going to check. From here to here, I would need to add 6,000. And if I add 6,000 again, I should get 3,500 or 35,000. Okay. Add 6,000 again, I should get 41. Add 6,000 again, 47. Population A is adding 6,000 a year. It is arithmetic. So to write an equation that defines population A, it didn't tell me what kind of equation to write. I could write it recursive, where the first year, the 0th year, is 23,000, sorry. And every one after that is the prior one plus 6,000. I'm going to write the explicit equation also, just because I think it's going to ask me about when are they going to overtake. I might need to calculate out multiple years. Yeah. So when I look at this, another way to do that is the nth equation, or an explicit definition. And if I have arithmetic, I'm going to go up to the top here and just refresh myself. Okay, I started with the 0th term, so I'm going to take what I start with, 23,000, my change, plus 6,000 times n. So 23,000 is the start. We add 6,000 however many years after 1990. Okay, so if I put a 1 in here, I'm going to take that 23 and add it one time. If I put a 4 in here, I'm going to multiply 4 times 26, add it to our starting amount, and then I've done that repeated addition. Now let's look at the same thing for population B. Let's see what's happening there, because then I see I'm going to have to write an equation here. Okay. So population B, if I am adding, I'm going to go here because adding to here is a lot easier. That's 750. If I add 750, I definitely don't get 5,400. Okay, so this has to be geometric. B is going to be geometric. Again, you can do that on your calculator by just doing some subtraction of one number minus the one before it and seeing what that difference is. Then that difference from the one before it is not the same number. And that difference from the one before it is not the same number. So, yeah, not arithmetic. Let's try geometric. I should be able to divide 3750 by 3125, and I get a 1.2. Let's just double check that the same is true for a different pair of numbers. If I take 4,500 and divide it by 3,750, there we go. There's that 1.2 again. So every single one of these, if I divide it by the term before it, I get 1.2. So it is multiplying by 1.2. So it's growing by 20%. If I think about like what they asked us in the top, it's growing by 20%. So an equation to define this, we start this one with a much smaller population. And then each year after that is the year before it times 1.2. As a nth term, an explicit equation, start times multiplier raised up to the nth power. We start with 3,125. We multiply it by 1.2, and we do that for any number of n years that we give it after 1990. Does B ever overtake A? This is a valid question, because what's happening is we've got things that start in different places and are growing at different rates. So if we think about population A, it's starting way up here at 23,000. And if you remember, it's going to grow in a straight line kind of graph. So it's going to be increasing just a little bit because it's only adding 6,000 per year. Population B starts way tinier. I mean, it's way down here. So someone might think, man, that's never going to catch up. But remember that if it's growing exponentially, exponential growth means it's going to start catching up here, and it is going to eventually get higher population than A. So I'm going to say yes. Anything that is growing geometrically, anything that's growing at that swooping up swoop like that, that is going to overtake something that's only growing in a straight line. So I'm going to say that the curve will grow faster after some number of years. Desmos would let us figure out how to do that. In fact, actually, our calculator can do it. It's pretty fancy. If you want to give it a try, I can show you. I'm just going to do it real quick on mine, so super fast. If you need to slow it down, go to your y equals. So from your normal screen here, go to your y equals. Type in your two equations. Of course, your calculator doesn't understand n, but it's here on this button right here. See that n? That is our variable button, so I'm going to use it. It's going to put it in as x, but that's the same kind of thing. Our second one gets raised up to the x power, so I did that here. So I've typed in my two equations. I always start with a zoom 6. It's a zoom standard window, so it'll take you from -10 to +10, -10 to +10. Now, I can't see a whole lot going on here because I need to be way up at 23,000. This window is at 10. I can't see much of anything. So I'm going to try this other thing. I'm going to just try a zoom, and I like to try this one. If you actually go up instead of down, one of your things you're going to find is a zoom fit. And that's going to just let the calculator try to get you something that it thinks is a helpful image. So I'm just going to hit zoom fit, and I just hit the enter button. Now here's that line that's growing straight. Here comes my exponential curve. Oof. And even that we can't see. I mean, it did a better job of showing me my two curves, but I can't see if it's really going to grow a whole lot more. So I'm even going to go change my window, and I'm going to make it even bigger. So right now, the x maximum is at 10. I need to see way farther over here. I'm going to put in 50. I don't know. I'm going to give this thing 50 years. And I'm going to turn this maximum up to something like 500,000. And now I'm going to try the graph button to see what this looks like now. There's my straight line. Here comes my curve. Again, this is 50 years out here. And there it is right there. I can actually find where that exact year that our second population becomes more than our first population. To find that, we can trace it and get kind of close, but right above the trace, you see that's a calculate menu. So second trace, it's going to take me to the calculate menu. There it is. I want to find the intersection, so I'm going to go hit number 5. And it asks me to get as close as I can on the first curve. That cursor is pretty close. I'm going to hit enter. Second curve is pretty close, enter. I don't feel like playing a guessing game, so I'm going to hit enter again. And it actually tells me that in the 21st, so into the 22nd year, they will both have a population at the same time of 150,500 of these, whatever these things are. And that's when they're going to overtake. So the graph we sketched matches the graph we can graph. It's pretty cool. It's a little deeper than we needed to go, but sometimes it's nice to see it. All right, 10.3, let's zip through. Finding square patterns. Define the sequence W. So W is the number of white squares in step N. Notice this starts with step 1. So I'm going to use the N minus 1 type of equation. All right. So W is the number of white squares, B is the number of black squares. Oh, they both change. Okay. I'm going to just start with some simple counting. As far as black squares, this one has 2 black squares. This one has 1, 2, 3, 4, 5, 6 black squares. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's weird. Looks like it's adding more to the side and on top each time. Ugh. That's going to be a weird pattern. Everything about white squares, I've got 3, 6, 7, 8, 9, 10. 4, 8, 9, 10, 11, 12, 13, 14. 2, 3, 4, 5, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, that's much more. I can see what's going on there. It's adding 4 each time. Oh, so that makes sense. Like when it's adding 4, it's like adding 1, 2. What is it adding? 3. Oh, it's like adding the 4 corners. Yeah, that's really weird. Okay. Well, anyways, the white is arithmetic. It adds 4 each time. An equation, if it doesn't ask me which one I want to do, I'm just going to go ahead and start with, I like the nth term ones. It's just easier to figure out. So for any number, I'm going to write an explicit one. I start with 10. I am adding 4 each time, but I don't add at the first one, so I need to have the n minus 1 because step 1, I'm not adding. Right now, if I put 1 in place here, I have 1 minus 1, which is 0. 0 times 4 is 0. That's how I'm still sticking with step 1 being 10 white squares. Now, I got to check if these black squares, they kind of, honestly, they've got me a little confused right now. So let's see, 6 divided by 2. Let's put a division sign in there. Obviously, that's getting 3 times bigger. This is not getting 3 times bigger. That's getting 2 times bigger. That's what's got me really lost. And I'm trying to picture how this is working because like these two would be like these two. So it's 1, 2, 3, 4. It adds 4 more. Adds 6 more. I'm sitting here staring at it and I'm kind of realizing that it's connected to like what step it is. On step 2, I did 2 times 2. And on step 3, I added 2 times 3. So I bet you on step 4, I'm going to add 2 times 4. I'm probably going to add 8. So each time we're adding 2 times whatever the step number is. I haven't seen something like that. I don't think it's been that complex. The black squares is in neither equation because we add 2 times n each time. It's based on the step number. And I mean, I can still write an equation for that, sure. It's going to be weird. It starts with 2 black squares. It adds 2n. But we have to add n minus 1. So that does look arithmetic, but it's not arithmetic. Let me plug in 3 and see if I have that right. 3 minus 1 is 2. 2 times 2 is 4. 2 plus 4 is not 12. So that's still not quite right. I actually don't know how to write an explicit one for that. I'm going to write a recursive. Our first step starts with 2. And then every step after that takes the prior one and it adds 2n. That's an equation that I can get. I've got that figured out. Okay. So if I were to take the second step, I take the prior one, which is 2, and I add 4 to it. That's it. Okay. Um, I don't know if the number of black squares will ever get more than the number of white squares. Here, I mean, they're closer. They're getting closer every time. Let's keep the pattern going and let's keep on seeing, because maybe that's a way to prove it. Each of these times for the white squares, it just adds 4. So I'm just going to add a couple more of these, 22, 26, 30, 34. Here we started with 2, then we added 4 to it, and get 6. We add 6 to it, we get 12. Now we're going to add, let's see, that's 2 times 2, that's 3 times 2, 4 times 2 is 8. We'll have 20. 5 times 2 is 10. Yep, right there. There it is. When we add 30 to it, or we add 10 to it, we get to 30. So yeah, this is how I know. Step 1, step 2, step 3, step 4, by step 5. More black squares than white. Oh man, that took me some thinking. Probably took you some thinking too. That's why they left this lesson for last. Alrighty, go tackle some practice problems. Maybe check out the lesson summary for a couple more examples. And keep on practicing. Thanks for watching.